Good afternoon, Build Stuff, and welcome back. We are still coming to you live via Vilnius from all over the world to all over the world. A big hello to all the folks out there in Lithuania who are joining us on site live, sat there at the Kinoplex with the popcorn and the soft drinks and watching all the stuff unfolding. I hope you're all having an awesome time out there. Hello to all the folks who are watching us live on Pine Tool, streaming all over the world. I hope you're all having an awesome time out there. And next up, it is my great pleasure to welcome to our Build Stuff virtual stage. He's the head of AI research at NASDAQ. He's going to be talking to us about entropy, mutual information, and prediction. Please give a big, warm Build Stuff welcome, Douglas Hamilton.
Dylan, thanks for having me, and good afternoon, everybody. So, as Dylan mentioned, today we're going to be talking about entropy, mutual information, and prediction, and more broadly, a topic very near and dear to my heart, information theory. We're going to be discussing it today in kind of a tactile way to get us to think like statisticians and think like data scientists and understand how we here at NASDAQ within our AI research group think about the science of prediction through the lens of these very important concepts. So without further ado, let's get started. So why talk about information theory in general? Well, information theory was developed really from the early part to the middle part to the late part really of the 20th century. Because in the 20th century, there was a boom in telecommunication technology, and engineers and scientists began finding themselves having to ask questions they've never really asked before, like, I have a bunch of words. How do I turn them into dots and dashes in an efficient way? If I want to send an electronic signal, how do I make sure that I can convert that electronic signal that was a sound back into sound? And once you start sending electronic signals, you start to wonder things like, well, lines aren't perfect. So when they come in, they're going to be kind of noisy. And how do I handle these signals even if they're noisy, right? How do I reconstruct them in reliable ways if they're noisy? And what this ultimately led scientists and engineers to in the middle part of the 20th century is an incredibly important question, which is, what the hell is information anyway? Right? And that's kind of a core question that's almost a little more philosophical than it is mathematical, at least at its precept. However, what information theory begins to let us do is talk about this in a mathematical way, which we'll see a little later. One of the other nice things about questions like this, and the fact that we're able to treat these in a mathematical way, is they have analogs in our day-to-day life and the ways we make decisions, both algorithmically with machines, as well as within the management structure of a company. Questions like, what information do I absolutely always need? How complex is my portfolio or strategy? And do I have the data to actually justify that complexity? What information can I ignore, and when can I ignore it? Is ignoring information, it turns out, really important sometimes. And of course, now that I have the data, what should I do? And these are the sorts of questions that we really want to answer with modern AI systems and modern approaches to data science. Before we jump in any further to start to answer these questions and discuss things with the language of information theory, we're going to need to take the typical way we think about the world and change it to make sure we're comporting with the way that data scientists and statisticians think about the world. So let's start by doing a simple thing like tearing asunder our concepts of how events work. So a very typical way that we think about the world is that we'll have an event. That event will go through some process and we'll have an outcome, right? And if this is our model of the world, then what we tend to focus a great deal on is the process itself. For example, I might go to the airport, I might get stuck in traffic, and I might miss my plane. And then I might have to talk to you guys from a Zoom instead of from the audience or auditorium instead. That's not what happened here. If that's how we think about the world, we become very focused on the process of getting to the airport. And that's important sometimes. However, as statisticians and as data scientists and artificial intelligence seers, we look at this model of the world and say, it's worked pretty well for the last few thousand years, but nah. And instead, we see the world somewhat like this. We have an event, and then we have a process. And that process can have numerous different sorts of outcomes at different levels of certainty. And when you look at the world like this, the process almost doesn't matter. And instead, what you focus a lot on is the event itself and then the outcomes. And you can treat the process like a black box. And so when we go forward and talk about entropy and mutual information and their application to predictive methodologies, we're going to spend almost no time talking about specific processes, that is specific, the way specific things unfold, but rather the inputs to that process and the outputs to that process. What we'll see later is when we say process, what we really mean is a model about how things work. This because we're relaxing how much we care about the process, it allows us to take many, many different and kind of novel approaches to how we model a process that might have almost nothing to do or look nothing like what actually occurs, but reliably map events to outcomes in very complex ways. Because we have this model of how the world works, that is, there are events and there are outcomes, and nobody actually understands why, we also have a new way that we want to talk about those outcomes. Using this notation, which if you remember back to your stats classes, you might remember, which is the probability of an outcome X from an event Y, or more formally, the probability of X given observation Y. So now that we've gone over these basics and gotten the language right, and know that we're not going to be talking about how specific items occur, but rather discussing the broad ways in which events impact the probability of outcomes, we can start discussing information theory, entropy, and mutual information, and the science of prediction. So let's start with entropy. I've been a quant professionally, right, data scientist professionally for about 7 years now. And if you ask most people who are kind of professional mathematicians how long they've been professional mathematicians, they'll tell you something like, the year they finished their bachelor's degree, their undergraduate degree, right? Maybe the first day they started their first job. If they're feeling really kind of saucy and want to impress you, maybe they'll mention that internship they had flipping burgers at Burger King because they had to count the number of times that the burger flipped in the air. But the reality, though, is that for most people in quantitative disciplines, you've been taking this stuff pretty seriously, probably since you were about 12 years old. And you've been learning, that's maybe the first time you encountered algebra, right? And you saw X plus 7 equals Y and it made sense, whereas half of the world's brains exploded and said, I don't want to do this anymore. So over time, when we study these quantitative fields, we tend to have building definitions of a thing that get more and more granular and kind of cover more and more edge cases. If you look at gravity, for example, you first learn about that it as a thing that causes apples to fall to the earth. Later, you might learn that it's the way large bodies interact with each other. And if you get high enough, you'll learn it has something to do with the way that mass affects space-time manifolds, right? Each definition builds on itself and gets more specific. This is not the case with entropy, though. Entropy is one of the worst and most poorly defined things in all of science. In fact, over the course of the last 20 years, here are some of the worst definitions for entropy I've ever heard. The first, which is very common, I'd say the most common, is simply defining entropy as chaos and disorder. If you've ever taken a differential equations course, you may have heard of entropy as this thing that kind of destroys the initial conditions of the system. If you've taken a thermodynamics course or maybe a chemistry course, it's sometimes also referred to as degrees of freedom. That's all well and good, but it doesn't really give you any intuitive sense of what entropy actually is, right? What does it mean that it destroys initial conditions? Well, if I'm talking about a differential equation, I know, but in all other cases, I don't. And it really doesn't mean anything that it's just chaos and disorder, because which is often described in analogy like, well, cars rust because of entropy, as if a rusty car is in some sense more disordered than a non-rusty one. And again, what the hell is degrees of freedom? So this is really the first great triumph of information theory that we'll discuss, which is a good definition for entropy. Entropy is, at its core, the sum of the probability of all events times the log of the probability of those events. Now, we'll dissect this a little more in a moment, but the key takeaway here is that what this means is entropy is the degree of uncertainty or randomness in a system. Key takeaways: that entropy is the degree of uncertainty or randomness in a system. This means different systems have different amounts of randomness and different amounts of uncertainty. That's pretty interesting. It also means, because we have an equation for it, we can, in some sense, measure the amount of uncertainty or randomness in a system. And if we can measure it, we can do interesting things with it, like make models, build programs, etc., off of this metric. Let's dissect it a little further. So it's kind of an intimidating equation when you first look at it. It's got the big sigma, it's got a bunch of little p's and i's in it. So what do they all mean? And it's got some kind of arcane symbols from set theory. Well, first, what it means is things that the more options we have for outcomes, the more random a situation tends to be. This should agree with our gut in a lot of sense. If you have a situation where every time you hand the barkeep, a euro, you get back a pint, well, that's not a terribly random situation. But if instead you play a game like barkeeper roulette, where you hand them a euro and then you throw a coin and hit a piece of ice or something, and you hit a random bottle on the back shelf, and that's what you get, that's a much more random situation. Likewise, the randomness of entropy is a function of the probability of outcomes. So if you have particular events that dominate, that is, that almost always occur, that sort of situation is going to be less random than ones where you have lots of events that tend to occur more often. Finally, we have this little log base 2, and I think this is the part that really that's really kind of the genius of this formulation of entropy, which is why base 2? Well, the reason we use base 2 is it turns out you can model almost any super complex vision of the world through a series of concurrent yes or no, is or is not questions. Anybody who's familiar with the decision tree knows that you can always make your decision tree deeper and get a more complex version of the world simply through, yes and no questions. So this is why we end up with an equation that looks like this. Things that have more outcomes are more random. Things that have differing probabilities of events have differing entropies. And we're going to talk about the world in terms of is not, and yes and no questions. Next, let's move on and discuss a statistician's two favorite toys, a coin and dice. So, and the question that I pose, and unfortunately I can't hear right now to answer, is which do we think is more random? A coin, which has 2 outcomes, each 50% likely, or a die, which has 6 outcomes, each 16.7% likely. Well, if we check our gut, we'd say that the coin is less random than the dice, right? I flip a coin, it could be heads, could be tails. I roll the dice, could be 1, 2, 3, 4, 5, or 6. Something about the coin seems, in some sense, less random than the die. And when we push it through the equation we saw above, that's exactly what we find. Our die has something called 2.6 bits of entropy, and our coin has 1 bit of entropy. And that is the bit that you're familiar with. That is, our coin has, in some sense, 1 bit of information attached to it, and our die has, in some sense, 2.6 bits of entropy. So now let's ask a more difficult question. Our gut could tell us very quickly that the coin was less random than the die. But what if we had a rigged die instead? So we still have 6 outcomes, but the 1 on the die has a 90% chance of occurring, and each of the others, 2, 3, 4, 5, and 6, only have a 2% chance. Which of these situations do we think is more random? Well, this is where our gut, it gets harder to tell just through a gut check. And exactly the sorts of area where we want, a more systematic way to look at randomness and uncertainty. It turns out that when we push it through the equation, what we find is that our rigged die only has 0.7 bits of entropy or information, less than the fair dice and less than the coin. What do we mean when we say that something has 1 bit of entropy or information, or 2.6 bits of entropy or information? Well, let's remember what we mean by bits. When we say a bit, what we mean is that it can be represented as a 0 or 1 with kind of one number, right? And 1 bit can represent 2 states, 0 and 1. When we say that a coin flip is 1 bit, what we mean is that we could write the results, heads and tails, onto 1 bit of information, a 0 or a 1. When we say that we have 2.58 bits of information in our dice roll, what we mean is we can write the outcomes into 2.5 bits. What we see here is exactly how we do that. On all the way to the left, we have our 1-bit coin flip, where we map a 0 to heads and a 1 to tails. Things get a little more complex when we start looking at our 2-bit, our dice roll, though. In the middle, what we see is something called an underfit dice roll, where we try to map our 2.58-bit dice roll to just 2 bits. We map a 1 to 0, 0, a 2 to 0, 1, a 3 to 1, 0, and a 4 to 1, 1. Now we're out of space. We can't put the 5 or the 6 anywhere. And so we've catastrophically lost information because we don't have a model of the world, a model of the dice roll, that is, that's able to actually capture all the information in the dice roll. What if we used another bit? What if we use 3 bits? Well, if we look all the way to the right, what we see is something overfitting. That is, we have more outcomes than we have more outcomes available to us than we have actual outcomes. And if we didn't know that, we might end up with something catastrophic in a different way, like saying that a 0 or a 7 are possible outcomes for our dice roll. But since we know that we can only have 1 through 6, we're able to solve this by taking 2 of the possible states and knowing them out for the time being. But this is why we describe entropy in terms of bits, because it describes the size of a model needed to contain all the information in a particular scenario. Now, scenarios can become much more complex than dice rolls and coin tosses. A coin toss is 1 bit of information. Dice roll, 2.58 bits. It turns out that if you want to model the days that it will rain over the course of the year in LA, that's about 170 bits of information. And it gets bigger and bigger from there. So next, we'll talk about conditional entropy and the power of information. We've already seen that a dice roll is more chaotic or more random than a coin flip, and a coin flip more random than our rigged dice. So now let's suppose we introduce a new thing, a new die, and we don't know if it's rigged or if it's fair. What is the entropy associated with that scenario? Well, it turns out a quirk of statistics that we don't have time to go into here is that this particular situation turns out to have the same entropy as our fair dice. This is because the number of ways that a die can be rigged, all the possible ways can be rigged, means that on average the die is fair. However, what if I told you that the die was in fact rigged? Well, now you've been given new information, and as soon as you get new information that the die is rigged, you know that it has less entropy and more certainty than the fair dice does. That is, information has, in some sense, reduced the total amount of uncertainty of the scenario we're looking at. You might be starting to understand where this is going in terms of the fact that if we have more information, we have less randomness, and if we have less randomness, we have more predictability, and that's pretty good insight. This is going to be very important later on when we talk about mutual information. But the key takeaway here is that this leads us to conditional entropy. The equation here is considerably more, is actually an order of magnitude more complex and intimidating than our first entropy equation. The good news is, unless you're a statistician, this is not what's important. Instead, what's really important here is the insight that conditional entropy, that is entropy, the entropy of an outcome X based on an observation or information Y, is always less than the entropy of the event by itself. I'm going to say that again in more plain terms. The total amount of uncertainty related to an event, if you've made an observation, is always less than the total amount of uncertainty from the event all by itself. Again, this will become very important later on. So let's look at an application of entropy within NASDAQ and financial services more broadly. Suppose that you want to mimic the exchange space, and you want to build a portfolio that tried to capture the returns within the exchange space. We say a portfolio, we treat a portfolio here like a model, because a portfolio is little more than a model of where we expect future returns to be for a set of stocks. So you look at the exchange space and say, the Intercontinental Exchange, who own the New York Stock Exchange, the London Stock Exchange, and NASDAQ are the 3 major players in this space right now. So I'm going to create a portfolio out of these 3 and capture the returns of the exchange space more broadly. The next question you have now that you've selected your constituents is, how should I actually weight these? Should I buy more NASDAQ than ICE? Well, I would say yes, but I might be biased. Should I buy more ICE than LSE? Well, maybe, maybe not. How should I mix these together in a sensible way to maximize my potential returns? And this is where entropy comes in handy. So it turns out that if we know nothing about the world, then we want to have a portfolio that reflects the fact that we know nothing about the world. Remember, we have made no observation aside from the fact that we want to be in the exchange space. We can take a sentence like that, I want to model the exchange space, but I don't know anything else, and turn it into an entropy equation. That is, we'd like to maximize the entropy of this portfolio of 3 stocks, NASDAQ, ICE, and the London Stock Exchange. To do this, we want to look at the constituents, or the weighting of each constituent, and do it in such a way that maximizes our entropy equation. This occurs when each stock is represented in equal proportions across the portfolio, 1/3, 1/3, and 1/3. What we might find out, though, is that we get special information. And that special information might be things like the entropy, like expectations of future returns, or market cap information, etc. And we'd like our entropy, the entropy of our actual portfolio, to match the entropy of our expected future returns, or of market cap, etc. And so when we construct our portfolio, we want to make sure that the entropy is reflective of the information we have. And this is really one of our first applications. This is a great application of entropy within the world of financial services and at NASDAQ more broadly. Now that we've spent a little time discussing entropy and the nuts and bolts of measuring uncertainty, we might ask ourselves a question. Well, we understand the world's uncertain. We understand we can use information to reduce uncertainty, but how do we actually make predictions, and how do we use information to reduce uncertainty? To do this, once again, we're going to tear some of our preconceptions about what prediction means asunder. So let's begin. Let's talk about 3 flavors of prediction. The first flavor of prediction I'm going to describe is a flavor of prediction that we're most familiar with. If I were to ask you, what's the stock market going to do tomorrow? That's something that we would all agree undoubtedly is prediction. We are, after all, in this case, predicting future information. By the same token, if I asked you to guess what number I'm thinking right now, or to read my mind in some sense, we'd probably say that that is also in some sense prediction as well, in that we're uncovering some hidden information, right? There's information that I know, the number I'm thinking of, and I need you to figure out what it is. Finally, and this one's probably the one that people don't most often associate with prediction, but I certainly would, is suppose that you're doing detective work. You're trying to figure out why something occurred in the past, why there's mud all over your floor when you get home, and your dog looks muddy when you get home as well. Well, this is reconstructing information about a past event which you didn't observe. This too is a flavor of prediction. And the reason this is a flavor of prediction is that they're all 3 of these are tied together by the same theme. That is, that prediction is the task of recovering hidden information from external observation. And so here's a model of prediction that we're going to use, that we use as data scientists. That is, we make an observation within an observation boundary using particular information, right? I'm looking outside right now, it's sunny. What's the likelihood that it will rain later? Well, hopefully pretty low, but it's November in Boston, and usually that means it's gonna rain later. So it's sunny now, a little lower, it's November, a little higher. And we use that information to try to figure out what's gonna happen in the future, which is of course hidden to us, something going on in the present that's hidden to us, or to reconstruct information about the past, right? Using the fact that it's sunny outside, we could try to predict whether it will rain this afternoon. We could try to figure out what the temperature outside is right now, or we could try to ask questions like, what's the likelihood that it rained last night, if you didn't know? And these are all different sorts of prediction tasks. In computer science parlance, this is the equivalent of, having a machine that predicts a future event, having a machine that looks at a picture and says whether it's a cat or a dog, present event, or having a machine that looks at a series of events and finds the root cause for them, reconstructing past information. So with this as our definition of prediction, let's play a simple game and understand mutual information as a form of information imitation. So this is going to be a really boring game, guys. Don't play it at home. People will stop liking you. You won't get invited to parties anymore, and they'll look at you strange. What we're going to do is we're going to flip a coin, and we're going to record the coin. Then we're going to flip a second coin. If it's not the same as the first, keep flipping it without recording. And as soon as it's the same result as the first coin, record it and stop the game. On the right, we see a couple examples of flips of this game. You flip a heads, you get heads as your final state. You flip tails or heads, then your second flip is a tails, so you have to reflip and get heads, and so on and so forth. So you know that the final state of the game is always going to be two coins with the same exact outcome. It turns out that what that means is that the first coin tells you an awful lot about what the second coin is, and the second coin tells you an awful lot about what the first coin is. And that these coins, so the outcomes are not independent. Why is this important for prediction? Well, it's important because if I know what the first coin is, I can predict with 100% certainty what the second coin will be. If I know what the second coin is, I can predict with 100% certainty what the first coin was in this game. And we have a very formalized way to measure the amount of information that knowing a piece of information like the first coin or the second coin tells us about the other one. And that is mutual information. Again, here the equation is a little more intimidating than our first one, so we won't go through it in deep detail. But the important thing here is this portion that's in brackets. Because what it tells us at our core is if two events, X and Y, are independent, then the joint probability of X and Y is the same, is equal to Px times Py, and the log of that is 0, so there's no information between the two. What that means is if two events are truly independent, then they don't give us information about each other and are not useful to make predictions. However, if X and Y are dependent events in some sense, then the joint probability is greater than the product of the independent probabilities, which means there's some information between the two. And again, here we say bits of information, because that is telling you how much uncertainty is reduced by this piece of information in a model. So let's go back and look at this again. We're going to flip a coin and we're going to record it. Then we're going to flip a second coin. If it's not the same as the first coin, we're going to reflip without recording. If it is the same as the second coin, we're going to stop the game and we're going to hide the coin. You can then ask for any one piece of information and guess what the second coin was. Any piece of information in the universe. Well, it turns out if we pass any potential piece of information you have through our mutual information equation, the piece of information that reduces all of the uncertainty in this is knowing the first coin. So that's all well and good. How do we actually use this within financial services at NASDAQ? So let's talk about strategy analysis. Let's introduce two very simple strategies that you could follow. One is a momentum strategy and the other is a mean reversion strategy. What we're looking at here is a pure momentum and a pure mean reversion strategy from 2016 to 2021 on the S&P 500. What's interesting about these two strategies is that they're exactly opposite. What a momentum strategy says is that the stock market went up today, it's going to go up tomorrow, so we should buy. And what a mean reversion strategy says is if the stock market went up yesterday, that means it's too valuable, so let's sell. If it went down yesterday, it's cheap, so let's buy. It turns out that these strategies are not exactly the same as each other, but they're perfect inverses of one another. And they have perfect mutual information as a result of one another. We can use these because they have perfect mutual information about one another as a basis to describe other strategies as well and understand them in terms of momentum and mean reversion signals. To give you a very, very concrete example of how this is used, when we look at alternative data and the signals that can be derived from alternative data, We use the concept of mean reversion strategies and momentum strategies very frequently. What we're looking at here is a project we engaged in where we used artificial intelligence to generate trading strategies in an automated way from alternative data. For those of you less familiar with the term, alternative data is a type of data which is not traditional financial data, but rather things like satellite images of parking lots and shipping lanes, bills of lading that tell you what's coming off a boat. You could imagine it as credit card receipts or cell phone telemetry data, et cetera, et cetera. And all of these might have information that tell us about stock returns. What we're looking at here is at the very bottom, a random strategy that just buys and sells stocks at random. In the middle, we have a whole bunch of alternative data streams that we've built simple strategies on, as well as one momentum strategy. And at the top, 2 AI generated strategies. So how do we use mutual information here? Well, the first thing we do is we look at all of those alternative data strategies in the middle and say, you know what? Those all share very high amounts of mutual information with a pure momentum strategy. So our clients are probably not going to get a whole lot of value out of them. Then we use that information further in a negative sense in order to inform an AI system that if we're going to construct a signal or a trading strategy out of many signals that are highly correlated with a momentum signal, we should do it in such a way that penalizes it for sharing lots of mutual information with a momentum signal as well. That allows the strategies that we generate to not just learn from the data that we have, but also learn how to deviate from that data in successful and smart ways. And what we see here is, what we like to say, is the lines that go up and to the right, the squiggly lines that go up to the right the most are our AI-generated strategies. And they do so in a meaningfully higher way and in a meaningfully different way than their constituent momentum signals. That is, we're able to learn the important things about the momentum signal without just copying it outright because we penalize it for being overly dependent or carrying too much mutual information with a momentum strategy. There's a few other interesting applications to mutual information that we'll discuss next before we close out. Before we move on to the closeout, we'll briefly discuss something called optimal guessing. This is really important also in many systems because a lot of the times, particularly in low latency systems, we don't have huge amounts of time to consider huge amounts of information. So we'd like to make a guess that's really good, really quickly. So let's introduce 2 strategies, a pure guessing strategy and an optimal guessing strategy. A pure guessing strategy is one that randomly chooses outcomes from all possible outcomes. An optimal guessing strategy is a strategy that chooses an outcome and is as correct as possible without careful study or exigent information. Think about it this way. If you show up to a multiple choice test and you just pick bubbles at random, that's pure guessing. If you show up to a multiple choice test and you always pick C, well, maybe that's optimal guessing, if C is more right than random. And that kind of brings us to our really concrete example of this is let's think back to our rigged dice. A pure guessing strategy on a rigged dice would be just guess a number, right? We're pure guessing, we don't know what's going to happen, so just guess something. However, an optimal guessing strategy here is to always guess 1, because it comes up the most often. In fact, if you always guess 1 on a rigged dice, we're going to be right 90% of the time. And what this means for us from an optimal guessing perspective is optimal guesses are models with only one output that maximize the mutual information between the model and the world, or the guess in the world, while having a minimally complex model. Again, let's say that again. An optimal guess is one that maximizes the mutual information between the guess and the world while minimizing the information of the guess itself. Because what's the entropy of something where 100% of the outcome is 1? Well, it's 0 bits. So we have a 0-bit model that maximizes the mutual information between the guess and the dice and is correct 90% of the time. And this is what we describe as optimal guessing. So you can create very, very simple programs that are run very, very quickly and are as right as possible. Finally, now that we spent some time discussing information theory in detail, mutual information, and entropy, we're going to get into some of my favorite aspect of it, which is discussing the rather interesting consequences that come from it. Again, we're going to look at some very basic assumptions that we make and think and see why thinking like statisticians and data scientists and people building models, many of these basic assumptions don't really hold up to snuff under our information theory assumptions. So let's start with the first one, which is, again, my favorite and the one that usually gets most people's head scratching. Causality. It's overrated. So the problem with causality is that causality is tricky and we don't always need it. In fact, if you have three events, A, B, and C, and A is causal of B and B is causal of C, then one of the things information theory tells us is, through mutual information, that B probably holds information about C. And you might ask yourself, well, why don't we just go understand the causal process between A and B? And surely that holds more information than between just B and C. And you tend to be right. However, there's many reasons why you might not be allowed or able to understand the causal process. Let's start with one. If you have, let's suppose you're trying to understand the sales of a company ahead of their earnings call. Well, it turns out that that's materially important information, and if you have it and you trade on it, at least in the US and the UK, you will go to jail because that's insider trading and it's super duper illegal. In fact, there's many sorts of information like this or knowledge of causal processes like this that you simply are not allowed to know. What we call this is confidential information or confidential processes. So A itself, or the process that brings A to B or C, might be confidential. So you're literally not allowed to know it or not allowed to use it. Another reason you might not actually understand A or the causal processes that lead to B or C is what I call irreducible complexity. There are quite a few situations and scenarios in the world that are so enormously complex that experts are merely pretending to understand the substrates of how things actually work. If you want a bit of a hot button topic, public health is pretty complex. I think we can argue about who's dealt best with public health over the last year and a half, but nobody's done very well, and everybody's models kind of suck. So knowing the causal information might not be the right place to focus on, rather than the informative information there. Finally, if for anybody who's ever been an astrophysicist, you know that when we want to learn something about a far-flung star, we don't build a rocket ship and go there. It would take huge amounts of time, huge amounts of cost, and be pretty infeasible to actually go to Alpha Centauri to learn something about Alpha Centauri. Likewise, if we want to learn something about how economies work, we typically don't just crash them for fun to see what will happen. That's because collecting information about the causal processes in these cases is enormously expensive. And due to that enormous expense, it's simply not plausible to understand in deep ways the causal processes that link A to B or C. So what we're left with instead is informative information between B and C that can be gleaned because they're both caused by A. Because they're both caused by this event A, our gut should feel good that they're related. And because we have information about how related they are, driven through mutual information, we should be confident that we can get useful information to predict C from B and vice versa because of the symmetry of mutual information. Next, we'll discuss my biggest bugbear in all of prediction right now, which is the information of rare events. When I interview data scientists, particularly at the entry level, what we oftentimes talk about is one of the projects they completed while they were in school. At some point, we'll talk about the data they have. And almost without fail, we'll eventually come across some set of rare events, some big outlier that they ran into. And the question I'll always ask is, well, what did you do about that outlier? And almost uniformly, the answer is, well, I deleted it because I can't be expected to predict outliers. This is terrible advice and an awful answer. Please don't give it if you're interviewing for a data science position. That's because information is not symmetric. And what we're looking at here is something called partial entropy, which is the information associated with a particular event in a set of events. And it turns out that an item with about a 90% chance likelihood of occurring holds the same amount of information as one with about a 1% chance of occurring. So that is, if you're going to delete 1% of your outcomes, you might as well delete 90% because they hold the same amount of information. But wait, it gets worse. There's another stat I like called the marginal entropy of observation. This stat looks at not the information held within a particular outcome, but within a particular observation or row of data. So suppose we have 3 outcomes, A, B, and C, with the probabilities noted there, or the frequencies noted there. And we have 1,000 observations. Then the partial information of our very rare event C is actually only a quarter, even though it occurs, 1/80th as often as A, has a quarter of the total information of A, and it has 20, and each observation has 20 times as much information as individual observations of event A as well. So they carry grossly more information than those in the more common occurrences. How do we use this at NASDAQ? Well, let's look at an example. Above, we're going to look. We currently are engaged in a pilot that looks at how we use AI to list options on our options exchanges. Our goal in this pilot is to make sure that we capture volume while reducing total contracts listed and the total messages that our systems have to process. Give you an idea why this is a problem. At the peak in 2020, NASDAQ across all of our options exchanges managed 1.4 million option contracts. That means we had 2.8 million of what we call puts and calls. That's kind of being long and short, or predicting that something will go up and down simultaneously. Because we have 2.8 million puts and calls, we have to have buy and sell sides, that is, people making buy offers and sell offers on each one. That means we have 5.6 million offers to buy and sell options at any given point in time. But it gets even harder, because our exchanges basically have to update all that information every, I think it's like 4 to 9 microseconds, which is pretty fast to update 5.8 million floating point numbers. This is incredibly taxing on our IT systems. It's incredibly taxing on the IT systems of a group of people we call our market makers. And it's incredibly difficult for retail investors, that's you and me, the common person interacting with the exchanges, to get our head around all of those strikes. So we'd like to simplify the strikes to make it a smaller amount in total. And again, it gets even worse, because most of those strikes never even trade. So it's just noise for noise's sake. Well, when we did this initially, we tried this at one point while ignoring rare events. And that's what you see up top here. And while it doesn't look meaningfully different in most places than with rare events that we see below, what we do notice is we have about 6 or 7 big spikes. And this is over the span of just over a year of trading days. We have 6 days that we really missed. We could ignore them and not get any better, but those 6 days actually account for 90% of our volume loss over the course of the year. We don't want to lose volume. Losing volume is expensive. At the bottom, we see what occurs when we actually take those rare events into consideration and give them due shrift, and good treatment. First of all, rather than losing on any given day 60 or 40+% of potential volume, we now never lose more than 20% of potential volume, grossly reducing our cost. There's an additional benefit. During one of those events, we actually figured out a much better way to list strikes, reducing the total number of strikes listed and reducing the total volume capture by a huge amount, which we see kind of in the middle of the graph there. So being considerate of these rare events, we capture much more information, and by being careful in their treatment, are able to produce a much higher performing model. This is an overview of how we at NASDAQ think about entropy and mutual information in the prediction process and the process of building and delivering AI systems. And that concludes my talk, and I'd be happy to take any questions at this time. Thanks.
Great stuff. Thank you, Douglas. I think we have, we've achieved complete enlightenment. There's a comment from Thomas saying, just based on your stuff about predictions and correlations, that a post-mortem is actually a prediction, which I rather like. But that's it in the chat. So thank you very much for that. Thank you so much for taking the time to join us online today and share your wisdom and insight with all the folks out there watching on the stream. Folks, anybody wants to chat to Douglas about any of the stuff that he's just talked about, please jump on the Zoom link, which we're about to drop in the chat on Pine, and you'll be able to hang out in there. If not, thank you everyone for watching. We're going to be back with our next session in, I think, just over 15 minutes. 20 past the hour, the next sessions are going to be kicking off. So we'll see all of you back there. Douglas, thank you again so much for taking the time to join us and speak to all of us today. There may be some folks in Zoom. If there are, say hello, see what they have to say. If not, thank you so much, and catch you at the next one, in person perhaps, who knows?
Hopefully. Thank you, Dylan. It was a lot of fun. We'll talk to you later.
Take care. Good to see you.